Hello everyone. So now in this video we are going to learn about central limit theorem. So we are actually at our fourth topic, and in the previous topic we have actually looked at distribution, and one of which, if you remember, is normal distribution. So it's going to have and if you notice, as what we mentioned last time, in statistics usually we are very used to seeing normal distribution, right? So if you see that normal distribution usually focuses on the whole population, right? So that's sort of like the essence of what we have learned earlier. So today we are actually going to look at central limit theorem. All right, central limit theorem, and you will see that how the central limit theorems actually sort of applies to a lot of statistical questions that we have. So just to bring you back to the normal distribution, so imagine now that we sort of have a large office building. All right, and in this building obviously we have individual rooms. All right, so these are the individual offices where, and the list goes on, and this will be the individual offices, and each of these individual office has about, say, 10 people. All right, so say now if we are going to get the number of days that the person or the employee is absent in a year, right? So what do we do about it then? How do we solve this question? So what you will do basically is to get the average score for each room, correct? So I have room 1, room 2, room 3, room 4, and so on. And after you have got each of this average score, and then you calculate the number of the individual office, and when you have the number of individual office, you just get the average score and you divide it by the number of rooms available. So what does this tell us? This actually applies to you getting number of days in which employees are absent. That applies to the whole population, right? Because it actually involves the whole office building here. So how is it related to central limit theorem? So what do we need to know about central limit theorem here? Central limit theorem basically tells us, if say we take a mean of a sample size of a certain size n, right? If we take a sample size, which means we take a portion of the sample size from this whole population here, and then we actually calculate the mean. All right, and when we calculate the mean, we actually plot the frequency of the mean. All right, and when you actually plot the frequency of the mean, what you actually get, right? So say we are plotting and all that, it tends to go by or adheres to our normal distribution. So if we just, let me just give you an example. So say if we just draw back to the example earlier on the big office building, right? So in our office building, we actually have, say, 50 rooms, all right? And earlier, remember that we mentioned that in each room over here, we actually have 10 people in each room. So this basically means that if we are going to get the number of days in which employees are absent for a year, for example, and then it means that I will actually have 500 data. And once I have got this, like we mentioned earlier, this actually applies to the whole population, right? So what central limit theorem tells us is that if we take just a random sample, for example, I take 10 different samples, yeah? I take 10 different samples, and let's take the sample size of 35, for example. All right, so what happens here is that I have a whole big building here, and I'm just going to randomly pick size um, of 35 data. All right, so my sample size n is actually 35, and in fact I'm going to go by sample 1. So I'm going to take randomly 35 data and I get the mean, right? And then after that I go with the second sample, in which I still go back and in the whole office building I take another random sample of size 35 and I calculate the mean. And then it goes on until I take a total of 10 different samples. So what central limit theorems tells us is that once you have got this mu, right, and then you plot all this data, eventually, so this dot here actually just indicates the mu that you get, or the mean of the sample size that you already get. So what central limit theorem tells us is that you actually tend to get a normal distribution. So this is actually very interesting. And it doesn't just apply to say a fix of 10 different samples, and it has to be a sample size of 35. You can even try it out. I mean, if you take an n of size 20 and you take 15 different samples of it, chances are you're going to get something of a normal distribution as well. So the only thing that could be of a difference would be the standard deviation. All right, of course, as we know, if the mean will still be about the same. So what this tells us is that of course the larger the size of your sample, the less your standard deviation for the sample. But anyway, so this is what it is about central limit theorem. So now how do we relate the central limit theorem to getting or to solve questions related to our statistics question, right? So if you remember, in our normal distribution, we actually have a certain formula in which you actually get a z-score, right? So for central limit theorem here, it actually says if you have a sample size of n, all right, and you actually randomly draw it from a population, and this population has a mean of mu. So by now you are very familiar with the symbol of mu and the symbol of sigma, right? Because sigma is the standard deviation, right? So this is according to your central limit theorem. So say you have sample size n randomly drawn from population of mean mu and standard deviation of sigma, all right, for a fairly large sample size, all right, in which your n is or greater than 30, all right, and this therefore actually has been proven mathematically that it adheres to this formula below here. So I'm just going to show you how we, if we recall the z-score from our normal distribution that we learned in the earlier chapter, it actually goes by x minus mu over standard deviation, right? So in this case, we still also remember that the sample mean in this case, so because earlier whatever that you have learned, you actually look at the population. So in this case, it's you taking samples from the whole population, in which you would just want to get a fraction of the sample and you see what happens and all that. So over here then, your central limit theorems, and when it applies to sample mean, it becomes x bar minus mu over sigma of square root of n. Alright, so if you remember this, so a new term for you that you see here is that this is actually the sample mean. Alright, and then this is actually mu. Mu is basically your population mean. Alright, this is your population standard deviation, and this is the sample size. Okay, so in fact, having seen this formula here, alright, so I hope you are familiar or you are able to differentiate what's the difference between these two. So basically, if you're just getting the whole population and all, that's where you take this. This is just our normal distribution. And if you are actually taking a sample, a certain sample size or a portion of the size of the whole batch of data that you have, then this is where you need to use this one here, which is z equals to x bar. Alright, so this x bar here is actually your sample mean. So let's look at an example. Alright, say, and this is actually extracted from our lecture note. So see now, say we have a mean amount of cash spent per customer at the tire and exhaust center is 78.2 with standard deviation of 7.10. If a random sample of 40 customers is taken, what's the probability that the amount spent by these 40 people is more than 3,200? Alright, so in questions like this or in all the maths question, I always like to look at what are the data that they actually gave. So in this case, you know that, alright, the mean, alright, is actually 78.2, right? And then standard deviation is denoted by sigma, is 7.10. All right, and then my sample size. See, now you have the mu, you have the standard deviation, and you take a random sample. So this is the keyword here. Random sample of 40 customers is taken. So in this case, your sample size is actually 40. All right, so in this case, you do know that this actually applies to this formula that we need to look at, which is this x bar here minus mu over sigma over cert n. All right, but now you see that over here, you want to get the probability of total amount that is spent is more than 3,200. So you want to be very clear with what it is. Yeah, I mean, you want to be very clear with what they actually give you. What they give you is mean, but the idea here is that they're asking you for total amount. So this basically means that we still need to get our sample mean, right? Because remember, the sample mean will then basically just be the amount spent divided by the number, right? So mean is just exactly the same as average. That's exactly what we're looking for. So in this case, they're giving us 3,200. That's the amount, right? We want to get the probability that people spend more than 3,200 here. So in this case, we will take the total amount, which is 3,200, divide by 40, and in this case, we get 80. Alright, so this is something that we actually need to calculate by ourselves according to this question. And now the substitution of what I have over here. Alright, so I already have my x bar minus my mu, 78.2, divided by my standard deviation. Standard deviation is 7.1 divided by square root of 40. Alright, this will give me approximately, I hope you give it a try at your calculator, will give me about like 1.6. And as usual, you go back to the Z table that you have, right? You're looking at probability of people spending more than 3,200. All right, so in this case, say this is 1.6. 3,200 amount spent basically translate into a sample mean of more than 1.6. All right, so from here you actually look at your exact table. All right, if you're looking at the table in which the area actually is shaded towards the right hand side, should give you about 0.0548. You might want to verify that. So basically it means that, what does this tell you? This is basically the probability that the 40 customers are going to spend a total amount of more than 3200. All right, so that's the essence of what it is. So you can see that the way for us to solve this question is actually just the same, only that you use a different formula when it comes to sample, right? So that's a little bit on what we actually know about central limit theorem. So in the next video, we're going to look at confidence interval.